Yeah, it's 10 years, no more than 10 years. More than 10 years. Yeah.
Ready? Yeah. Okay, perfect. Welcome everyone to the first ICG Lab Talk series event for this semester. It's a pleasure to have Professor Christoph Heinzl here, who we already know for some years, at least I know him. He's a professor at University of Passau now, and he did his PhD at TU Vienna in the field of visualization and analysis of industrial xCT data, so computer tomography data, and he got awarded the habilitation, the venia docendi, also from TU Vienna in 2022, and he's currently, so after that he moved from to the professorship at University of Passau, where he is currently a professor for cognitive sensor systems, and he's leading the research group for knowledge-based image processing and visualization at the Fraunhofer IIS Development Center for X-ray technology. So it's a combination of a university setting plus Fraunhofer. And yeah, we're looking forward to Christoph's talk. As usual, we have 45 minutes of presentation. Then we're going to have 15 minutes for Q&A. And please also use the chat for asking questions. Whoever is here can of course just raise the hand. And with that, I'm looking forward to Christoph's talk, and you can take it from here. Thank you.
Thank you very much, and warm welcome also from my side. Yeah, Christoph Heinzl is my name, and yeah, today I would like to show you a little bit of what we did in the area of visualization and analysis of xCTing data, and mainly we're using this for decision making in various aspects. So before I would start, I would like to give you a little bit of an overview of me as a person. What did I do so far? If this is working, does it work? Okay, then do it that way. So regarding my education work experience, I did a little bit of a different way that you are used to. So first I studied automation engineering. I went 4 years into industry, and then I thought, okay, this cannot be it. There must be more. And I started my doctoral studies at TU Wien. In parallel, I got appointed a research fellowship at University of Applied Sciences of Austria. And since then, I was dealing with X-ray computer tomography data. I went through the career path here at this university. So yeah, I became senior researcher, then head of the research center. And in parallel, I also started some teaching in both facilities where yeah, I was on the move in 2022. So I got appointed to professorship at University of Passau, and this goes hand in hand with the group lead at the Fraunhofer IIS Development Center. So this is a rather unconventional setting, so to say. It brings some advantages, some disadvantages as well. But with this setting, I can follow basic research as well as applied research in this direction. So a little bit of an overview in terms of teaching. What do I teach there? So we have lectures on visualization and data visualization. We are about to start immersive analytics also in Passau, and cognitive sensing for the next year. We're giving some seminars and also some projects. Or maybe a question to all of you. Who knows Fraunhofer? Yeah. Fraunhofer is basically an applied research entity. Yeah? And the IIS is one of the largest Fraunhofer institutes we have. And this is also where we are located with the Fraunhofer Development Center of X-ray technology here in our main building in Fürth. So basically we have a couple of different sites, Fürth, Würzburg, Deckendorf, and my part is Passau. This is a division of the Fraunhofer IIS. IIS, some people may know as home of MP3. So we're doing a lot of codec stuff here at IIS, and also a lot of non-destructive testing in our division. So that's why we have a joint venture here, more or less, in terms of non-destructive testing as well. So my group is dealing with knowledge-based visualization and image processing. So basically, we are focusing on big data analytics. What is big data for us? So when you go for a large-scale xCT facility, then typically you end up in single data sets of 50 terabytes. This needs to be processed on commodity hardware, not on this kind of laptops, but it should be processed, for example, in a regular workstation. And this is somehow also the loop where we would like to end up in my group. So basically, first of all, we are doing xCT simulation. So this means a digital twin of the xCT device. We also have a focus on compression and decompression because we want to handle these large data sets. For sure, we need segmentation and quantification in this respect. And with me as person, also the visualization aspect is coming into the group. So just to show you a little bit of these research areas, we offer simulation as a service. So basically, we can generate fast 2D projection images of arbitrary specimens. Why are we doing that? Because we want to estimate scanning parameters. We want to have ground truth for AI systems. And here we are dealing mostly with the topic of physics-informed AI. For sure, we also offer the standard techniques like estimating spectra, computing probability of detection analysis in this respect. As I said, the compression is of high importance when you're dealing with that large data. So we came up with a three-dimensional wavelet-based compression scheme for volumetric data. And we always have the discussion like, is it lossless? Is it not lossless? Yes, our compression is lossy. We call it visually lossless because we can tweak the compression level in a way that we can say, okay, it's fair enough for the respective analysis task. In terms of feature extraction, we are interested in very large data sets here. For example, this is a CT scan of a complete car, which we did at our main facility in Fürth. And this facility is used for crash tests. Why is it used for crash tests? What do you think? Well, when you disassemble the car after the crash test, all the parts fall off, and you don't know how it's damaged. When we look at it in place, we can see how critical the damage is. And our collaborators, which are Bavarian automotive manufacturers, I don't want to say any names here. They are interested in segmentation of individual elements such as spring components or other parts of the car. Good, but we are here to talk about visualization. So I would like to give you an overview of what I did in this area. And my research profile in this regard is quite diverse. It's ranging from scientific visualization to visual analytics. At the core of my work, there's interactive visualization of spatial and quantitative data. So basically everything which we get from our devices and which we extract from our devices. The second largest area is the visual parameter space analysis. So whenever you use an algorithm, you want to tweak it, you want to get an optimal setting in terms of the input parameters in order to get the best possible output for your application area. In order to do so, you also need some comparative visualization techniques as well as ensemble visualization techniques. In my PhD, I also did some uncertainty visualization. Interestingly, this is coming up now even again, but from a very different area. And for sure, we also did some visualization theory and modeling in this respect in my work. All of the techniques which we implemented, we need image processing and feature extraction. And in future, I'm working more in terms of time-varying data as well as human-computer interaction. For today, I would like to focus on these two areas where I have selected a couple of papers and respective techniques, which I would like to show you in the upcoming 45 minutes. Good. So in my research, I strive for answering the bridging research question: how can we visually analyze and explore rich xCT data? I come to that in a minute, what I mean by rich xCT data. Just out of for completeness here, the references which I would like to present to you now in the following chapters. Okay, let's dive into the first chapter of interactive visualization of spatial and quantitative data. So typically, when we address a visualization problem in this area, we follow a design study methodology. Some of you may know the design study methodology of Sedelmeier et al., who are saying that we have a three-phase regime, which we are following here, consisting of a precondition phase, a core phase, and finally an analysis phase. In terms of our problem, we first start off with a learning phase. So basically, we need to know what is available in the visualization literature, what is the focus of the respective techniques before we can start with the next step. Next step is we know. This means we have to select promising collaborations. So, for example, do I need somebody who's active in, I don't know, machine learning, in GPU programming or whatever? Do I need a domain expert, for example? For sure, we need a visualization expert in this direction. Finally, I need to cast the roles. So basically, then the setup is complete and I can start with the core phase. The core phase starts with the discovery. So basically, the discovery means here you address various visualization techniques together with your domain specialists and have a look which fits most to solving your problem. This is always a longer discussion phase. And only then when we are roughly there where we say, okay, this is suitable, this is reasonable, we want to implement it, we start with the actual design of such a prototype. Good. Until that point, we did not program a single line. So only at the point of implementation, there the action starts. For sure, we also need to implement our tools. We need to provide them accordingly. We need to deploy them for our domain specialists. In the final phase, we have a reflection phase. This means we analyzing our hypotheses, reflect about them, whether they hold true, whether the visualization techniques were valid. And then we have a write-up phase, meaning we have to write a respective paper or a documentation out of this project. Good. In terms of application area, as I said, I'm active in the visual analysis of rich xCT data, mainly from complex materials such as fiber-reinforced composites. In the video, you can see one of these samples. So these are very small samples, like a centimeter in height. And we have to do a full rotation in order to achieve a full CT image. The generated CT image you can see on the right side. And there you will find, for example, the interesting areas, epoxy resin matrix, fiber bundles in the different directions. Then you see the pores in the matrix and also the pores in the fiber bundle. Why are we interested in these structures? Well, fibers are the structures which are carrying the load. Pores are nice because they don't weight anything, but they will destroy our specimen when they are under load. So we need to characterize those features in detail. So what we are doing is we set up a processing pipeline, which is starting from the xCT scan. Then we have the conventional 2D projection image generation, which you know from your medical doctor. We reconstruct it finally to a 3D data set. In the pre-processing phase, there we actually segment the features of interest. We are labeling them and finally compute the individual characteristics. So for example, we can see here pores, and the domain specialists are interested here in a number of 25 characteristics per feature. This can be a center point, this can be an extent, this can be a volume, this can be a surface, shape factors, whatever you need. Good. And together with the original primary data, so primary data is everything we get out of the device. Yeah. We build up a rich xCT data structure or data element, which holds the data volumes, which holds the segmentation masks, which holds the label images, and also these feature lists. And the question now is how to actually visually analyze this rich xCT data, right? Good. So the research questions we are tackling here in this area are: what are the most important feature characteristics? What is the relationship between these? Can we visually connect features by the characteristics? What are suitable techniques to filter, explore, and connect feature sets? Which visual metaphors can be used to encode, abstract, or reconfigure sets from features of rich xCT data? And finally, which interaction concepts work and support respective analysis workflows? Good. When you have a look at the related work, related work in this area is comprised by 3 areas. So basically, in the very first branch, we have the general concepts. In the design of visualization systems, we have the visualization techniques for interactive visualization of spatial and quantitative data. And finally, also visualization techniques for material science applications. So my contributions to computer sciences are found as follows. So basically, these are visualization design studies and visualization techniques for this field, mainly for spatial and quantitative data. So we came up with techniques for exploring data, for encoding data, for visual classification. At times, you also have to abstract the data or reconfigure it and do the explicit encoding. According to Yi et al., the paper towards a deeper understanding of the role of interaction in information visualization, you could classify these techniques into the categories of explore, of connect, of encode, of connect, of abstract and elaborate, of reconfigure, filter, and finally encode. What does this mean? Explore means show me something else of my data, right? Encode means show me a different representation of my data. Then connect means show me related items. Abstract and elaborate, more or less detail of my data sets. Reconfigure means show me a different arrangement of my data. And finally, filter means something, show me something conditional. What is not seen here is select. Select is marking something of interest. Good. So one visualization prototype, which we integrated in our open source framework OpenIA, is the FiberScout, which you can see here. The FiberScout is basically such a combined system. We have a 3D view, we have a scatter plot matrix, we have parallel coordinate plots, we have a polar heat map, and these are all linked in order to achieve respective analysis of this fiber reinforced polymer data sets. So what you can see in the video, you select specific fibers in, for example, as shown here, in the scatter plot matrix. The respective fibers are highlighted in the different views. And once you have finished with it, you can dig deeper in your data set and refine your choice. Good. Next up, in terms of encoding, even for such a simple data set as we see here, this data set holds something like 11,000 fibers. Visual clutter significantly blocks our analysis. So if we have a look at this data set, and if I ask you what are the preferred directions of these fibers, you will have a hard time telling me, right? So, but when we know we are interested in directions only, we can go for an abstracted version of this representation. So basically what you can do is you can exploit the metaphor of a polar plot. A polar plot encodes the features in terms of 2 angles. Here in this case, theta and phi. And every fiber has these angles in space. So we move from the Cartesian coordinate system to a polar coordinate system. Problem here as well is you will end up in overplotting, especially if you have like very nicely aligned features. So that's why we extended this concept with a polar heat map, which aggregates these contributions in a heat map so that you can easily see where you have the preferred directions of these fibers in the data set. Good. Also, that is fully interactive, so you can do a selection here. What is marked here, for example, are fibers are oriented along the x-axis but tilted to the z-axis, and you get it highlighted in the different views as well. Occlusion can also be an issue for visual data exploration in a way of viewpoints. So the classification of viewpoints, especially for this kind of materials, is an issue, especially when you have like a layered structure of the material. This means when you, or what you classify as a good viewpoint is a viewpoint where you have a lot of overlaps. So basically the structures are all behind each other, right? And this is what you can see here in the first image of this pore data set. When you look at the sample from the top, you have a lot of visual clutter. You don't see the individual layered structure, and this is what our domain specialists were interested in. So how can we do that? Yeah, we can abstract these viewpoints in a way that we come up with a visual metaphor encoding the quality of each viewpoint. Yeah? So basically, all the information you can see right here, here's the mouse, all the information right here to a single element, for example, a cylinder encoding your quality metric. How do we do that? We classify the gray values of our data in terms of strongly overlapping pixels, partly overlapping pixels, and not overlapping pixels. Yeah, this is what you can see in this formula, and this is a single value which you can encode on the surface of a sphere. We experimented here a little bit with different variation of this viewing sphere. So every visual metaphor has its advantages. For example, the color coding on the surface of the sphere gives you an overall impression of data values which you actually don't have because they're interpolated, whereas these sticks give you just the data values you really have computed. At times, also the spatial binding is a really critical issue. Yeah, so here again, a very simple data set, 108 pores we can see in this data set. And from our first look, these pores look all spherical. Yeah. So I would guess asking you draw an average representation of these pores. Yeah, you all would come with at least an ellipsoid, maybe a sphere. In our mean objects approach, we could visualize that this is much more complex than what we see at first sight. So how are we doing that? We are reconfiguring our dataset in a way that we register each element over the other and then see how strong they contribute. So here we can see that in detail. So we have here 5 different elements which we want to register over each other, which are forming the basis of such a mean object. So basically, you just overlay the elements and count the contributions. For example, in the central area, you have all the 5 data sets contributing, so you will yield a value of 5 in the sim. Whereas, for example, here on these edges, we have no contributions unless this data set, for example, in this arc coming out. Why are we doing so? Because these structures are important for finite element simulations. Maybe you have heard of it. This is a technique of computing like the behavior of a material when being in use. And it makes a difference whether you consider these pores as spheres or whether you integrate a real probabilistic shape into that in that finite element simulations. So in our mean object, you can have areas of high probability, medium and low probability, and it's up to you to extract an isoprobability surface to be used in a finite element simulation. Another technique we were exploring is was focusing on 4D CT, so spatial temporal variations of a specimen of interest. Again, these are industrial processes. Consider, for example, a heat cooling cycle, or consider a dry out process going on in your sample. And the question is how to visualize this process going on. Yeah? And our take on that in fuzzy feature tracking was to come up with a visualization system which first characterizes the different event types. Event type in this case means we first detect a new feature. Another event could be a continuation, so the feature was there in the first step and is also prevalent in the second step. Or it can dissolve, it can split, it can merge. And this is what we encode here as color. So basically, violet means here we first detect the feature. Orange means we see the continuation of this feature, and so on and so forth. And with that kind of representation, you can keep track of what is going on. Nevertheless, we were satisfied in terms of the analysis of the process. So what we were then implementing and adding here is a tracking graph of this process. Yeah? You can see that in the very first step, you track a lot of events going on. Yeah? And then during the process going on, there have been a lot of these events, which or a lot of these features which dissolved, for example, or merged in this respect. Yeah. With our tracking procedure, we employed an overlap-based metric. This allows us to assign a probability or an uncertainty of this tracking step to the tracking graph. So we encoded that as a transparency. So whenever you see not a solid or saturated color, then the uncertainties are much higher than in the saturated areas. Good. Yeah, for sure. We also have to evaluate these techniques. Yeah. Typically, we are doing that with domain specialists in visualization, but also with specialists of the application area. I know these are not as big as you're used to from InfoVis or Visual Analytics, where we're dealing with like hundreds or more experts in this area. But this is what we have, and this is what we have to live with. Yeah. In the typical case, we are doing questionnaires, we evaluate them in Likert scales, and with that you can see, for example, the polar plot was very well received of these techniques, which I was showing before. Good. In the next part, I would shift focus a little bit towards visual parameter space analysis, as well as comparative visualization and ensemble analysis. And I know in visualization, these are all distinct fields, yeah, but in my application areas, they really belong together, yeah, because we, for the visual parameter space analysis, we always want to do an output analysis. Yeah? How can we do that? With comparative visualization, right? And as we have rather complex data sets, I would call it even ensemble analysis. That's why it's not just comparative visualization here. So the problem statement here is also fairly easy. We have a model, we sample the input parameters and get respective outputs. These outputs need to be analyzed. So basically, visualization can be a great help in this process of inspecting the relations between input and output, as well as to visually compare the generated outputs. This is what we are aiming for. And mainly for the areas of segmentation algorithms or pipelines, as well as reconstruction algorithms. And some of these I would like to show you in the remainder of the talk. So again, we start with an xCT scan. We generate the data, and then we have a black box. A black box which contains the reconstruction or segmentation technique. The outputs which we have here are 3D volumes. We have discrete label data. We have parametric representations of our features. So for example, an ellipsoid, a cylinder, or a fiber. This is what is referred to here as a parametric representation of these features. And also these lists of features which we want to analyze. The problem when you do such sampling of your parameter space is that you have a high number of these ensemble members, and they are all just slightly different. So you need to compare it on various layers. Good. So my tasks are here twofold. The very first one is to do this input-output analysis in the visual parameter space analysis. And secondly, the question is how to do the comparative visualization. So research questions we are taking here in this field is how to compare these large, slightly changing data sets. What is the relationship between input parameter space and potential outputs? What are potential trade-offs in these parameters? Are there, for example, specific parameters which I can neglect? Or are there parameters, for example, where I tweak just a little bit and get a completely different result in the output? For sure, we want to encode, for example, the similarity of the different features. Now, the related work in this area is even wider and spanning from visual parameter space analysis, the comparison of respective data, basically, could be time-oriented data, but it's also spatial data, comparative visualization techniques, as well as visualization techniques for ensemble data. And some contributions on my side are here found in this area, as I said, for the purpose of reconstruction and segmentation techniques. So we came up here with similarity measures and analysis techniques. Furthermore, comparative visualization techniques on the parametric objects, but also in the for the spatial data, correlation analysis, as well as histogram heat maps for ensemble data, as well as ensemble analysis using dynamic volume lines. Again, when you have a look here at Sedelmeyer's paper on visual parameter space analysis in this conceptual framework, you can classify the techniques in terms of their navigation strategies from local to global or global to local. What does it mean? Local to global in the sense of Sedelmeyer means that you start with a first try. You set the parameter space once, let the system run, then you get an output. And from that, you dig deeper. You refine your parameters and do the next one. Global to local, on the other hand, means you compute everything up front and then explore this vast data set. So this is somewhere where my techniques are located, I would say. Good. In terms of the workflow, basically, we start with such a rich set of data. First of all, we have to select one data set as a reference data. Why do we have to select one as a reference out of the set we want to analyze? Any idea? Well, we don't have a ground truth here. Because CT here in this respect is already the best technique you can apply. So you have to do a relative comparison. So what you do is you set one data set as a reference and compute the similarity to this reference for all the other elements in the set. Finally, you want to explore and visualize the respective data, and this is what we're doing in the visual parameter space analysis. So, in order to start with, for the similarity computation, what I need first is a similarity metric. And even for this rather simple case of these fibers, we spent quite some time in order to figure out what similarity metric is suitable and what is optimal in this case. So what can you do? For each of these objects, we have, for example, characteristics. We have a start point, we have an end point, we have a center point, we have a diameter, we have a length of this feature. And a naive approach would say, okay, let's consider all these elements spanning high-dimensional space. So for example, if I have one coordinate, two angles, and the length, this would span a six-dimensional space. And comparing one fiber with the other one would boil down to computing the Euclidean distance, for example, between those elements. But then you would say, okay, these are very different physical characteristics. So how can we compare that? It doesn't make any sense. Yeah. So we explored the field a little bit more. We came up with differences in point distances. Yeah. Since we have star-centered endpoint, we can compute these distances and see how similar they are. Yeah. But as we have something rotationally symmetric, yeah, you end up in a high dissimilarity if you have a perfect match, but just rotated when one element is just fully rotated. So the method of choice in this respect was to compute an overlap metric. Yeah, so basically to sample points within the one element and see how much of this is contained in the other element. By doing so, you can come up with respective numbers for this overlap metric, seeing how much is contained in the other one. Good. I will skip now the similarity measures. So just to see this rotation invariance here for these point distances, but I will not go into details. I would rather want to show you the prototype here in this respect. So this is another module of OpenIA. It's called FIAC, implemented by a PhD student of mine. And basically, it contains a result list. Some of you of the institute should know this representation or have at least an idea where we took inspiration of. So this was inspired by Grazl-Leval's lineup tool. Yeah, so basically you have here the quantitative values, for example, here the fiber scouts, but you can add additional quantities in order to sort the data sets according to your quantities of interest. We have here a spatial view in order to compare the data sets with each other. We have a correlation matrix in order to inspect these metrics against each other, and then a whole load of parameters for the experiment as well as for the prototype. Good. So for the similarity analysis, as I said, we followed the ideas in the lineup tool. So basically, we have a name, we have a 3D interactive preview of the spatial data set. We have the quantitative values of interest, in this case, the fiber count. And what we extended here is also a histogram encoding those similarities. So you could see how well they coincide with your reference. So for example, for the very first one, this is the reference which we selected. We have a perfect match. The other data sets are more and more dissimilar from this original data set or reference data set. As I said, in terms of correlation analysis, we opted for a scatter plot matrix, because just you can see how these metrics perform against each other. You can exploit them and select the metric of interest for your problem. A rather new approach, which we have just published as a preprint. This is not yet published in a conference. There we are seeking for a new definition or distinction of similarity analysis and uncertainty analysis. Because in the visualization community, what we are doing is often referred to as uncertainty analysis. You tweak here a little bit and see basically how uncertain your result gets. But in our application area, everything is fully defined. We have our model, which is fully defined. You tweak a parameter there, you can see the respective output. So that's why we rather opt for encoding that as a similarity, or terming that, or coining that as a similarity, a sensitivity, I have to say, and we are seeking for this difference. The paper is coming together with a study, a study prototype called Sensitivity Explorer, and this is parametrizing reconstruction process going on. So a parametric reconstruction process of these fibers. So what you can see here is basically an overview of these parameters of the respective algorithm. You can see here in these black areas that, for example, this first parameter has big influence on the output parameters. Yeah, so here input values, here output values. You can explore that in more detail. So in terms of each individual element, yeah, which is important for tweaking your reconstruction algorithm. And in order to explore the selected parameters sets which you want to consider, we opted for doing a star sampling around the selected points. Yeah? Why do we want to do this star sampling? Because with the star sampling in the input area, you immediately see how strong these values are changing in the output area. So here you can see, for example, 2 of these stars, yeah, in the input of this algorithm, and over there another one. And when you have a look at these stars, so for example, on the output side, we don't see too much variation of these points. So this is the first considered one. When we have a look at this more outlier star sampling, you can see that we have a very strong variation on the output here as well. Good. We also want to do a comparative visualization. So we are interested in having a look at various of the results we generate. And according to Gleicher et al., there are 3 different concepts of comparative visualization. So you can do juxtaposition, a superposition, and an explicit encoding. A superposition we can see here. So this is basically overlapping 2 data sets on each other. It's a straightforward way of doing this visualization. And even so, with only 2 data sets, yeah, you will need a certain time to look at it to figure out where we have the differences. Yeah. When you do the same thing for the explicit encoding, you immediately see where we have a very high dissimilarity. I don't have to tell you a lot about this visualization technique. Yeah. So this is of importance for us, and that's why the explicit encoding is integrated here in this prototype. For all of the methods, we also seek for generalizability. Yeah? So basically, yeah, this can be in terms of the objects we are interested in. For sure, we can also compute this for spherical objects, no doubt about that. But the more recent work of another PhD student, she is into linearization of n-dimensional data and comparing those. Yeah. So what we are doing here is we take these lists of characteristics, abstract those to a 1D value with multidimensional scaling, and the proximity of points to each other tells us how similar the objects are in the spatial domain. Good. The final thing I would like to show you is the comparison of volume ensembles. So volume ensembles, as I said, we have rather small deviations in the individual gray values of these elements. Yeah? But we want to know where they are and how big they are. Yeah? So this is an initial example. It's just a very simple data set, which you can see here. And we just apply the Gaussian filter, everything increasing sigma on this data set. I guess you would see that between 0.6 and 0.8, there's a difference. Yeah, but how to quantify, this is another story. You would have to invest quite a lot of time to figure that out. So the goal is here to compare the complete 3D volumes and to find regions of high variations. We are not interested in regions which are similar or which even do have the same value. Yeah? What should we analyze there? We are just interested in those areas where we have a lot of variation. So we did a very bold move, and said, okay, let's linearize volumes. Great idea, isn't it? So when you linearize volumes, you extract a line profile per volume and plot it into a diagram. Yeah. Why are we doing that? Yeah, because line profiles we immediately see where we have a lot of variation and where we don't have any variation. Yeah? So you would agree, for example, here we have a lot of variations, here we have less variation, and here, yeah, we don't care basically, right? Why is that? As I said, line plots are more intuitive and easier to understand in terms of these intensity differences. And positional encoding is much more effective than if we would just do a color coding on the surface of our object. Good. So the question would then be how to do this line profile extraction. We opted here for going for a Hilbert curve. Hilbert curve always follows the direct neighbors of your volume, which means that we can directly compare the individual voxel indices with each other, which is nice because if you would do the same thing, for example, for a satellite scan, yeah, you always have these jumps from one line to the next and from one layer to the next, right? And this is what we don't want to have because you have then areas which you cannot compare. Good. So we thought, okay, yeah, nice, let's do it. Here you can see a sample of a 16 cubed data set yielding 4,000 indices. 64 cubed, already 262,000 indices. And if we go for real world samples, yeah, 1K cubed, 2K cubed, yeah, far off of this big data sets, which I was referring to before, then we are already at 1 billion or 8.5 billion of these indices. And I don't know which kind of monitors you have, but for ours, the horizontal screen resolution is simply not sufficient. So we have to come up with a intelligent scaling of these line plots, right? Again, let's go back and think about what I introduced before. We are interested in those areas where we have a lot of variation. We are not interested in the areas where we don't have any variation. So our take on that was to compute the local ensemble variation. So basically to compute how strong these points are changing from each other. Yeah. So for example, this has then been computed for each and every index, right? Out of that, we derived an importance function. Yeah. So we want to consider those areas more where we have a lot of variations, and we want to consider those areas less where we don't have too much variation. So we use the cumulative importance function in order to scale these graphs, right? And this is what we call nonlinearly scaled Hilbert indices graph. So there you can see that we squeeze those areas where we have not too much variation and extended those areas where we have large variation, right? Good. In order to keep track of this scaling process, we also integrated here scaling widgets, so you can see nicely color-coded. For example, these black areas, they are strongly squeezed and the other ones are extended. So these appear brighter in this variation. Here you can see this implemented in the prototype. You can see the comparison of 6 data sets with each other. We have here a tracker so that you can see where you are in the data sets and which areas we compressed, which others we did not compress. You can brush in these line plots in order to reveal where these areas are then in the spatial domain, right? Now you may argue that, okay, now you can just compare 6 data sets. Well, we implemented here also functional box plots. This means we compute the minimum, the maximum, the mean, and the upper and lower quartile out of the plots. And this way we can integrate as many of these plots as we want, right? Good. Well, but still we had a problem, yeah, because this was simply not enough. So we need to have a more severe compression scheme, and this is why we came up with histogram heat maps. In the histogram heat maps, we subdivided these graphs now in segments of equally sized bins in terms of the Hilbert indices and also in terms of the intensities. Yeah? And for each area here, we just counted how many data points are going through respective block, so to say, right? When you encode this in color in terms of low frequencies, so this means we don't have any data points in there, or high frequency means we have a lot of data points in there, you have a rather good feeling of what is going on. Yeah, and this we integrated in the prototype and made it dynamically. So if you zoom into the data, then we dynamically switch to the line-based profile whenever it makes sense. And as a first overview visualization, you get this histogram heat map. Such techniques we evaluated using case studies. For example, here in this case study, we have a foam data set, and the hypothesis was that the main variation of these 16 reconstruction techniques applied in the data sets is, for example, in the strut areas of the foam, right? So what we did is we brushed in the line plots all those areas where we have large variation, and quickly identified that this matches also the strut areas. Good. With that being said, I would like to conclude. As I said, my research integrates design studies, techniques, and visual metaphors for interactive visualization of spatial and quantitative data. We have seen some of these techniques before, and also the visual parameter space analysis, comparative visualization, and ensemble variation. I would like to give you a sneak peek into what we are currently working on. This is what we call cross-virtuality analytics. Yeah? This is one area we are following, and the other area is machine learning. Not because everybody is doing it. We are doing it because we need it in order to classify the respective features of interest, extract them, and classify them according to our needs. And for the cross-virtuality analytics domain is the motivation is that the data is getting more and more complex, and typically you are not analyzing it alone anymore. So this setting is kind of outdated, that the expert is sitting in front of a monitor. You have a number of experts, they want to use, for example, AR headsets when they are on the shop floor. They want to use VR devices, for example, when they're in this design office. And they still use the conventional desktop setup. But how can they collaborate? How can you ensure seamless collaboration between those people? And furthermore, what happens if they are not co-located, if they're not standing in the same room, if they are, for example, on different continents? This is what we are interested here in this area. As I said, and for the machine learning, we are interested in things like feature extraction and classification, as well as physics-informed AI. I have here a short video for demonstrating this first step into a VR prototype of immersive analytics. It's called AugmeNDT. And this is doing basically the same thing as we've seen in the FiberSculpt module right in the second section of the first section of the talk. So basically, it comes up with various interaction regimes and visualization techniques in order to explore and analyze this data. So we start off with a three-dimensional data set. You can see it here. It's the same data set you've seen in the system before. We have here this model in miniature metaphor, which is mounted basically to your controller, and you can select the areas of interest. We have an exploded view so that you can dive into your data. And finally, we come up with visualization techniques in order to explore the similarity of interesting regions. And also the domain specialists wanted to have conventional infovis techniques, which we organized in a book metaphor, which you can bring up and use for data analysis. Good, so that's about it. Thank you very much for your attention, and I would be happy to take your questions now.
Thank you. Time for a couple of questions. Thank you, Christoph.
Welcome.
Who wants to go first?
Yeah.
Maybe it's not very specific collaboration, but so for your collaborations with creating this the variant that most of the students should be Like how do you get your user tasks in your data? Do they come with concrete user tasks to you? Do they come with data that they generated themselves, or use public data sets? Is there some pipeline when you say, if we have this data, we could visualize this and solve these tasks, and we integrate this into their factories, or how is this?
Well, you know these guys, you always have to push them a little bit. Yeah. Actually, for these large scans, the XXL scans, yeah, there was a larger Bavarian project out of which we could build up such a facility. Yeah? So this is a really big facility where you can drive in with cars and trucks. Recently, we scanned a helicopter. And this was also a very nice experience, yeah, because when you did the scan and you know, okay, it should not have anything, but you're a little bit concerned whether the helicopter arrives again. Anyhow, so the idea behind that activity is we have a lot of applications where we have larger samples than usual. Yeah. Consider, for example, container scans. Yeah, you have the large harbors, they are getting like 10,000 of containers a day, and you want to inspect what is in there without opening it. Yeah, so this is a motivation for that. Automotive industry is another motivation for that. I explained a little bit the crash test scenarios. I mean, such a scan is costly. If you lose something in your car and want to have a CT done, we have to charge like 50,000 euros. So I don't know whether it pays off. But anyways, if you consider this in contrast to a crash test, yeah, with all the preparation, with all the handling afterwards, yeah, we're talking easily of like 100,000 of euros, and this is just cheaper. Yeah, it gives you more information than what the original crash test would give you. Because from that data analysis, the automotive people can learn how their methods work, and they can improve it according to real data. Yeah? So this is a big benefit. And another application area which is targeted for this device is aeronautics, for example. In aeronautics, yeah, for sure, you have very large parts. Yeah, you have a lot of these composite components. And in recent years, we have seen that more and more functionality is integrated in a single component. Yeah? So, for example, a component which was made in the 2000s out of 100 parts is now one single part. Still, it has to prove that it fulfills the complete functionality. Yeah? How would you do that? Yeah, you need a big CT system. So we said, okay, yes, we can. This is the story behind this xCTing.
There is a question online. Is this, by Alexander Huber, is the segmentation of the first topic done manually?
Well, the segmentation, we are doing it in various ways. Yeah, the simplest case for sure is just a thresholding. Yeah, in some applications this just works. Yeah, whenever we have decent data. Yeah, in a lot of applications, as for example for this car data set, it does not work. Yeah, because you have a lot of artifacts in there, you have a lot of noise in there, you need more sophisticated segmentation techniques. Yeah, so it's an algorithm, or these are different algorithms which we're using, typically problem driven. It's not a manual segmentation whatsoever. In a way that yeah, you're doing some in-painting and gets the respective feature marked. So yeah, for the spring example, this was an active learning approach for example.
My questions are several ones, but I'm just picking one. So you mentioned when we discussed it before that the data sets are up to 50 terabytes.
Yeah.
How do you render that? What's the pipeline? I mean, you have like a data storage and you have a machine with a GPU, probably.
Well, this is a very good question. We are working on that. At the moment, we are in this compression step, which I was showing in the very beginning. Yeah, There we have a multi-step regime of this data set. So we can provide it in coarse resolution, and you get like a multi-scale visualization for free by the compression. Yeah. So actually we're using standard technologies. Yeah. But we want to directly work in this compressed format. Yeah. We cannot do everything at once, but this will be an upcoming step.
Okay. Oliver?
Yeah.
A very specific question. So basically for that overlap distance metric that you mentioned, is that correct? Because you can have very little volumetric overlap, having fairly aligned fibers and a much larger overlap with very usable. So would it be more correct to use the similar minimum cost by the party matching of the volume?
Well, as I said, we explored a lot of these metrics. But in the end of the day, when you're working close to the application, you have to explain this metric. Yeah, and the selection of the overlap-based metric was then done basically on demand by our main specialist.
This is probably incorrect. Did you explore basically the point matching method as well? I'm not talking about that one that you explained. That is of course incorrect also. If you pick specific points and have the match, but I'm talking like these traditional minimal cost third-party matching methods that you use in ICT, where basically you're matching and computing the minimal distance of best match points.
Yeah. A good direction for future research. We did not explore it further because our focus was on the visual parameter-based analysis, and for us, this was basically one component which we had to fill, which we decided together with the domain specialists. They were fine with it, so we went for that. Yeah,
so probably don't know these techniques.
That's for sure. But as I said, our interest in this regard was to help them improve their algorithms, and they could do that with the existing metric. Maybe it's not perfect. Yeah, this is for sure. But they did not have anything before that. Yeah, they just did by hand. Then they ended up in a list of 30 parameters. This was reduced to 20 being hard-coded somewhere in the code, and they did not know, does this have an effect in the final result? And so with this technique, we could give them at least an overview of what is happening, yeah, according to the metric they pick. And they were picking the overlap-based metric as primary choice.
The other one was not.
Yeah.
But other question on slide 22 with your polar plot.
Yeah.
You know that the resolution, you have a polar plot being projected to a circle area, and there's a resolution inconsistency. You have basically a low resolution at the border and in the center. Does that matter?
Just a moment, I have to find my mouse. Where is it? How was this thing set up? Ah, here it is. Slide 22, you said.
If you're projecting the polar coordinates on the circle, and then you have, of course, a lower resolution at periphery than the center. Does that
not too much. So basically, they are interested in like 2 degrees, 3 degrees, something like that, but not a very coarse or a very fine resolution in this placement. Yeah. So the idea is to figure out what are preferred directions, which is what they can see there. And a method which I did not explain here is also the clustering of areas where they have a similar behavior. Yeah. So this is what is of interest to them.
The data and the polar coordinates of the vertebrae we have to solve and couple.
Probably, yeah.
I think Andreas was first. Yeah.
Yeah, so in your example with the xCT data, we always have one intensity value per voxel. I think we constructed.
Well, also that is no more true.
Yeah, because I was interested, I know from material science that a lot of people combine tomography with spectroscopy or diffraction. And then you have a whole spectrum, the voxel, or
Yeah.
did you work with this kind of thing?
Yeah.
And if some of your approaches are generalizable.
Answer to the first question, yes, we did. Actually, we had a project where we implemented a NanoXCT device, which should not just do attenuation contrast, but also do like elemental CT. And there at each spatial point, we computed this, spectra. So this can be done. We did also a module on that in a way to analyze the spectra, to reveal the materials in the three-dimensional domain. Where do we have a preferred material, and also to reveal the material decomposition. Yeah. Maybe coming back to your first question, attenuation contrast is the standard technique which is commonly linked with CT. But there's also phase contrast you can have a look at. So, for example, where are the interfaces? You can also have a view on dark field contrast. This means, for example, if you have a lot of minor structures which you cannot resolve in your data set, give a strong response. For example, if you do a tomography of sugar, yeah, and you cannot resolve the individual sugar grains, then you would have a very strong response in there. Then there's key edge imaging. Yeah, when you know which material you have in there, you can look at a certain key edge of your spectrum. Yeah, and this way you get the material parts corresponding to a specific element. And apart from that, you have XRF, where you can generate single spectra or diffraction imaging. So it's a large umbrella of data, and it's complex. It's nasty to handle because when you have the data, you start over. You want to extract features of interest. Yeah. And this is what your domain specialists want to see and want or know and want to evaluate.
Okay, thank you, Christoph. In the interest of time, we have to close the session, so Christian, maybe you can ask your question offline. Yeah, thanks again to our speaker. And with this, I'm closing the session. I have to mention that the next invited talk is going to be on the 22nd of November. We have a colleague from Cambridge, Raphael Matthew, and he's a professor of graphics and displays. And that's what he's doing research on. Will be again very interesting. And yeah, please sign if you're part of the seminar. For those who are online, we took note about your participation. And with this, I'm closing the session. Thank you, Christoph, for a super interesting talk.
Thank you.
Thank you.